Let us look at bonding. In this particular module, we will be answering what is bonding, why we need bonding, how bonds are formed, and what are the different types of bonds. Let us recall what is orbit and what is orbital. Orbit is also called as KLM, shell is the path. Each orbit is placed at a particular distance from the nucleus. Orbital is the shape of the object inside which electrons are placed. This is what you would have studied earlier. These are historical information. We need to look at more recent developments. The term orbit is based on Bohr model. According to Bohr model, electrons are able to revolve in certain orbits having definite energies around the nucleus without radiating any energy. But it could not explain the emission spectra of all atoms except hydrogen. So, this model became obsolete. You need to come out of this orbit concept because we now know electrons are not confined to any orbits. Orbital is not a place where electron is present, but a place where there is maximum probability of finding one. So, we can say orbital is a probability distribution function of finding an electron. Before we move forward, we need to understand the different approaches being followed by different people in different fields to study the same thing. Let us look at how a physicist and a chemist look at things. A chemist looks at electron as a particle, whereas the physicist treats electron as a wave equation. For a chemist, orbitals have definite shapes, S, P, D, F orbitals you are already aware of. But when we talk about a physicist, he talks about contour map when he discusses orbitals. The chemist mainly focuses on electron. In other words, the study of organic chemistry basically revolves around electrons, whereas when we talk about physicists, they study about waves, heat, subatomic particles. Chemist focuses on entire process, that is the reaction from the starting material to the end product, whereas physicists many times focus on individual steps. The chemist uses mathematics only for theoretical approaches, whereas physicist uses mathematics in most field of their study. Chemistry is practical or application oriented, whereas physics study basics and fundamental processes. Many mechanisms have exceptions. Say for example, we have Markovnikov rule and anti-Markovnikov rule. We have Zaitsev rule, we also have Hofmann rule. So, we have many exceptions to known mechanisms, whereas in the physics, exception to the laws or rules are not common. In order to have a better understanding of chemistry, we need to know the difference between what is non-observable and what is observable. When we draw a chemical bond, we often write like a line or rod. Let us say we have an atom A and this is having a bond with atom B. So, this particular line what we draw is called the chemical bond. But for all practical purpose, there is no such line that exists between the atoms. Does it mean there is no such line connecting the atom? We said we cannot observe the chemical bond, but we can measure the bond length. The distance between the two atoms we can measure. This way, we can indirectly say that the two atoms are held together by a connecting force and it is called a bond. We cannot observe the orbital or individual electrons. We cannot observe orbitals or individual electrons, but what we can say is electron charge densities are observable. The 3D volume where the probability of finding of electron is more is called the orbital. We cannot see bond order, atomic charges or polarizability, whereas we can measure electrical dipole moment and magnetic dipole moment of the molecules. Similarly, aromaticity is a concept which is non-observable, whereas NMR chemical shift for the benzene protons can be studied. Similarly, hybridization is a concept which is purely a theoretical one, but same bond energies of CH bond in CH4 is actually the observable phenomena. Similarly, excitation is a non-observable phenomena, whereas photoelectron spectra is a observable phenomena. Let us move from Bohr model to a newer method. Our understanding is going to be based on quantum mechanics. We will be discussing largely qualitative and conceptual models rather than mathematical description. Erwin Schrödinger developed a theory. He was awarded Nobel Prize for his theory. Energy of a moving electron can be expressed in terms of mathematical expressions. These mathematical expressions are called wave equations. They define the state of the system at each spatial position and time. A wave equation has a series of solutions called wave functions. Each wave function corresponds to a different energy level for the electron. Although the solutions are approximate, this helps us understand the atomic and molecular structure. Let us come back to atomic orbitals. We will look at the modern description. In the previous slide, we saw the solution to the wave equation does not give the exact location of the electron, does not talk about the speed of the electron. It gives probability of finding the electron at any particular place. The region in space where an electron is likely to be found is called an orbital. They have different shapes, size and orientations. When we say degenerate orbitals, these are orbitals that have same energy. Let us move on to quantum numbers. We have 4 types. They are called principal quantum number, angular momentum quantum number or azimuthal quantum number, magnetic quantum number and spin quantum number. The symbols of the same are represented here. These are called as principal quantum number is n, angular momentum quantum number is denoted as L, magnetic quantum number is denoted as m sub L and the spin quantum number is denoted as m sub S. And the possible values of principal quantum number are 1, 2, 3, 4. In the case of angular momentum quantum number, they start from 0 to n minus 1. And in the case of magnetic quantum number, it starts from minus L to 0 to plus L, and the spin quantum number has only 2 values, either plus half or minus half. Let us look at what is the principal quantum number. The principal quantum number describes electron shell or energy level of an atom. This depends on the distance between the electron and the nucleus, that is the radial coordinates are given as r. This denotes shell number. The angular momentum or orbital quantum number L, this describes the subshells and gives the magnitude of the orbital's angular momentum through the relationship. This specifies the shape of an atomic orbital, and this strongly influences the chemical bonds and bond angles. This basically denotes the orbital. The next is the magnetic quantum number. This describes the energy level available within a subshell. This denotes degenerate orbitals. It is associated with orbital orientation. Then the last one, which is a spin quantum number, this describes the spin of the electron within the orbital. This has 2 values only, corresponding to spin and opposite spin, that is parallel spin and opposite spin. Let us look at the shapes of the atomic orbitals. Here we see the quantum numbers are assigned to orbitals. The principal quantum number is written first, followed by angular momentum quantum number, followed by the m sub L, then m sub S. The first number 2 represents basically the principal quantum number. The second letter represents the azimuthal quantum number, and the subscript represents the magnetic quantum number, and the 2 electrons which are present in this particular orbital can have plus half or minus half spin quantum numbers. So, when we start with the number n equal to 1, that represents basically the s orbital. So, in this s orbital we can have maximum 2 electrons, and when the principal quantum number is 2, we have 2 subshells 0 and 1. So, 0 represents s orbital and the number L1 represents minus 1 0 1, that means we have 3 magnetic quantum numbers. So, that represents p orbitals px, py and pz. Each orbital can accommodate 2 electrons each. So, we have total 6 electrons in the p orbitals, and when we move on to the next quantum number 3, the principal quantum number 3, we have 0, 1, 2 the azimuthal quantum numbers we have, and correspondingly 0 represents s orbital, minus 1 0 1 this represents p orbital, and minus 2 minus 1 0 1 2 this represents d orbital. So, we have 5 d orbitals which can accommodate total 10 electrons. Let us look at the shapes of the atomic orbitals. We have s orbital which is spherical in shape. We have p orbitals, 3 p orbitals as shown here. We have 5 d orbitals. What we see here is a representation view. Let us look at the orbitals' real structures using hydrogen wave function. The numbers within the brackets are quantum numbers n, l and m sub l. If you look at here 200, 300, these are all the numbers we are looking at, and when we have n equal to 2, that represents 2 s orbitals. When l equal to 0, that represents s orbital. So, this is the shape of the s orbital, and when we go to 300, when the angular momentum quantum number is 0, that represents basically the s orbital. So, this is first letter 3 represents the principal quantum number. So, 300 represents 3s orbital, and when we move to the next one 210, that means 2 is the first principal quantum number followed by azimuthal quantum number, then magnetic quantum number. So, this is representing 2px orbital, and when we have 310, that represents basically the 3px orbital. When we have 311, that represents 3p y orbital, and here we have representation of d orbitals as well.